refactoring. We don't modify the text directly, we work with this PSI. And that's how it looks like. So there's a small code sample, and we have a PSI class here, and it has one PSI method. And for a comment, there is also some node, PSI doc comment. And actually, for every single token here, there is a separate node. For example, there are a lot of PSI keywords here. And for every single non-token for a whitespace, there is also a node. So everything else is just an instance of PSI whitespace. So in our tree, we have the information about all of this, and we can use it in our code. And when the code has to modify something, it has to take care about all these nodes. It has access to them, but it has to handle them differently. Because in each code, in each single refactoring, in each single quick fix, the task is completely different. So we have to basically support, for example, preserving the comments in a different way, unfortunately. But to ensure that we don't forget about that, we have a special property-based test that opens random files, inserts random comments into them, then runs random actions, and checks that the comments are still there. And we found quite a lot of bugs this way. So, the next challenge is cross-language references. So, a compiler usually handles just one language, be it Java or Scala or C#, whatever. But user projects normally contain files in different languages. For example, here we have an XML example from Spring Framework. XML is also a language. And in this case, it contains a reference to a Java file. And so the IDE should take care of that. And if you rename this Java class, it should update this reference. So how do we address that? We have a unified notion of reference, applicable to all possible languages that our IDEs support. And yeah, my examples are mostly Java and XML, but this all applies to other languages. They are quite similar. So a PSI reference just says that in some PSI element, in some range inside of it, there is a special reference. And if you call the most important method of it resolve, it will work for some time, and then it will return you the element where this reference points to. And that's how go-to-declaration works. You just press a shortcut, and it finds the reference at this correct location and invokes resolve, and then navigates you to the PSI element. And that's also how refactorings work. If you, for example, move that Java class that reference points to, then the refactoring will find all those references to this element and invoke the bind-to-element method with the new location, and the reference will update itself. And I should note that the reference resolution, unlike the compiler, works bottom-up. The compilers usually process the file as a whole, and they just walk in a top-down fashion and resolve everything they meet. They maintain some symbol table to help for that. But for an IDE, it might be very profitable to find just a specific reference and resolve only it without everything else, because everything else would be expensive. This is useful during go-to-declaration or during find usages when you have to scan a lot of files and want to spend as little time in each file as possible. But references use some caching inside, so this is not a big performance problem. Okay, next challenge also relates to supporting multiple languages, but this time in a different way. For a compiler, a string literal is just a string literal, nothing else. But for a developer, it might contain whole another language inside of it. In this example, it's SQL. But it can also be Java, regular expression, or anything else. And it does not only apply to the string literals, it also applies to comments sometimes, and XML tags, and so on. And the IDE has to support that, because the users like to have their refactoring also not break things, even if those things are referenced inside string literals. So we have to provide code analysis, highlighting completion for string literal contents. And how we do it? Well, we just write a lot of code to do it. We identify the places and the languages we have to inject, and note that it can be not just one string literal, it can be a concatenation of string literals, and it can also include variable references, and then we should understand what the values of these variables are, do some data flow analysis. Then we finally get the resulting text of this string passed into some method probably, and we create another PSI tree, so we parse it separately. And then we run the whole IDE smartness on that PSI tree. And we, of course, don't forget to make back to the source. And there are some interesting challenges, because the source might look differently from the PSI tree that is parsed, due, for example, to character escaping. But it's not a rocket science, it's just a bunch of code that does it. Okay, next challenge. It's again about several languages, and this time languages sharing the same backend. For example, the Java virtual machine. It has not only Java language compiled to it, but also Scala, Groovy, Kotlin, whatever else, Clojure. And the problem is that all these languages can refer to each other, because on runtime it's just the same bytecode. And the IDE has to support them. For a compiler, that wouldn't be a very big issue if first Groovy class is compiled, then Java class, then Kotlin class, then Scala class, in this example. Then the compiler would just see this all as class files, and class files have unified format, and all these compilers obviously know how to parse that. But we are not a compiler. We don't reuse it. We're an IDE, and the class files might not just be there, or they might be outdated, because the user has not compiled yet. So we have to work with the source code. And to support all these languages, we have to provide a common underlying PSI model for that. And the solution is that all these languages have their own PSI with their own interfaces and so on, but they also pretend to be a bit of Java. They all provide implementation of Java-specific interfaces like PSI class, PSI field, PSI method, parameter type, and so on. And we have an API called findClass, for example, to which you give the qualified name, and it returns you some PSI class. And the plugins all plug into this functionality and just return their own implementation of PSI class. And once you have all these interfaces, as long as they return correct results, it shouldn't matter for resolve which language these classes, fields, and so on are in. Okay, I think, yeah, the next challenge. It's working with invalid code. A compiler, when it meets an invalid code, is totally justified to just stop at this point. Maybe some smart compilers continue analyzing the file until the end and report several errors, but that's it. But the IDE, in IDE, broken code is a norm. When you write in the code, it's broken 90% of the time because it's incomplete. And the IDE still has to be helpful in that situation. For example, code completion, like here. It should suggest some variant, even if the declaration of that variant happens to be after the broken code. And how do we address that? We have error recovery in our lexers and parsers and so on. And in our PSI, it's totally okay to have a method without a body, method without a parameter list, and so on. And all clients should check for that. So, for the error recovery is usually quite simple. The requirement for it is that it should support common scenarios that happen during typing the code. And in case of Java, like here, it's just a matter of if you see something unexpected, just skip it, try parsing again, and until you see the closing brace. In other languages, it is sometimes more challenging, but if you have handwritten or half-generated parsers, as we do, then you usually can write code that handles it. So one requirement is that the IDE should support common scenarios. And another requirement is that the IDE should never fail, never ever. Even if the user accidentally pastes some XML or binary content into a Java file, which might happen, the IDE should never fail. And the IDE should produce some PSI tree. The parser should produce some PSI tree covering the whole text. It may consist only of a special PSI error element with messages like declaration expected, but it should cover the entire text. And again, we have a special test for that opens random files and does random things with them, pastes random texts, deletes random text, and we see that no exceptions are thrown neither from the parser nor from code analysis. Okay. Another thing with invalid code is that we require even more smart analysis. For example, you have written a call to method, but forgot to specify the arguments. Actually, you decided that you don't like the method name and want to rename it. And for a compiler, that's just an error code. It's not a reference to a method. And if we had to work by language specification, we'd have to do the same. But unfortunately, we are much more flexible than a compiler, and we can provide a special kind of reference that still results to this method, although with a special mark that it's not an entirely valid result. And this is quite a useful functionality because it can also be used by the code highlighting to highlight things in red, and code completion as well to sort the results. So it's great. Okay, and I think now we are at the end of the first part, which was about the competence, the features that distinguish IDEs from the compilers. And now we'll switch to the performance, which is how to make everything fast, or at least not very slow. And performance is actually an area where I spend quite a lot of time, because I have a laptop, which is great, I like it, it's very compact, convenient, but unfortunately it's not very powerful. It doesn't have a lot of memory, so I often see that the IDE is slow for me. And I always run with Profiler, I look at the snapshots and try to understand how to fix the issue. And that's how I spend most of my time. So, the performance. As you can see, it will consist of two major subsections. Again, the fact that the IDE should deal with the code modifications, and then I'll talk about how we handle large projects. Okay, the compilers just read your code again. But the IDEs modify your code themselves, and they should also be prepared to the code being modified by an external process like Git or the user typing. And suppose you have an editor with a background highlighting running, and then you press a button. And what should happen? First, how to model the change? Should the PSI be mutable, or should a new PSI be created? What to do with the highlighting that's currently running? It should probably not observe the PSI being changed while it's running because of possible race conditions and inconsistencies in the logic. And anyway, that highlighting is not useful anymore because the code has changed and you have to restart it. So what do we do in this case? We have, that's not the part I'm proud of, but it works most of the time. So we have mutable PSI. This means that if you had a class in a Java file and you went to its name and typed a letter, then you will have the very same PSI class object, but its getName method will now return something else. But whenever you have something mutable, you have a problem. Because whenever you have something mutable and multiple threads, because you have now to synchronize things to prevent race conditions. And we have a very simple approach to that, namely a global read-write lock. So many threads can read at the same time, only one thread can write, and nobody can read one while somebody writes. And this model is very simple. It makes writing the code of the IDE quite simple, but it can lead to user experience degradation. Because when you're typing in the file, that's a modification. And that's you should have a write log for that. But to grab the write log, you should first ensure that no one else is reading the model. And there might be many threads that are currently doing some analysis. And we can't stop these threads. We can't interrupt them right away because they would leave something inconsistent. So we gently ask them to stop when they find it convenient. And a normal behaving thread would just call a special method called checkCancelled, and it should do it relatively frequently. And this method could eventually throw an exception if the thread has to be terminated. And usually during code highlighting, it helps. So when you type a letter, we notify that all other threads must be stopped, and when they called that checkCancelled, they are stopped. But unfortunately, some threads are not very well behaving, and in this case, you get a user interface freeze. You press the button, but you're waiting for that write lock to be able to be grabbed, and you're waiting for it all the time that some background thread is working and not calling these special methods. And yeah, in sometimes it can last several seconds or maybe more. We try to overcome that, but we're still not there, sorry. Next challenge, also related to code modification, is that once you have typed that letter, we have to update the code model as fast as possible. And we start with incrementally updating the lexer used for syntax highlighting in the editor and the parser used for the PSI and the whole analysis. So for the lexer, the task is relatively easy. The lexer has a notion of state, and in some states, the lexer says that I can safely be restarted from here, and we remember the offsets at which the lexer can be restarted, and we find the closest such offset to the changed range, and we restart the lexer from there. For parser, it's a bit more interesting because our parsers are not incremental by design. They just process whatever text they are given, produce a tree, and that's it. But the PSI they built, it supports incremental reparse. There are some special kinds of PSI elements that have special type where you can ask if you can reparse or not. For example, if you type in a Java method, then the IDE will get the current PSI of this file and find the closest such reparsable element containing the changed range. Usually it's the code block. And it will then ask the code block if, so, dear code block, here's the new text. Can you still handle this text? And usually the code block says yes. Sometimes it says no. If you, for example, have typed a curly brace that breaks all the balance of braces. But most of the time it's yes. And in that case, the parse contents method is invoked with the new text. And just the contents of this code block are replaced. And if the code block said no, we just can go to the parent and ask it if it can reparse itself. In the worst case, we go up to the file and reparse the whole file. Okay, the next challenge is much more challenging. So you had a file open. It had a lot of references. Every identifier in a Java file, almost every, is a reference. And they are all resolved during background highlighting. And resolve can be quite expensive. So result is cached. And you know, there are two great problems in computer science. One is naming things, and the other is when to invalidate the cache. And here we have precisely the same issue. And the problem with that is that resolve method is just some code. It can be written by anyone from any plugin, any framework support can contribute a reference. And inside it can do anything. Normally references depend on the contents of the current file, or maybe on other files in the same project, on project settings, like the Java standard library version being used, and so on. But there are some crazy references that depend on any random file on the disk. Some even go to the internet for resolving. And so we cannot track what the reference depends on. We do not track what the reference depends on. And that's an issue. So we have no solution to the problem of reusing the cached references. We just clear all the cache for all references on any PSI change. That means that when you type anything, the whole file has to be re-resolved. In some languages, there are ways of optimizing that, though. The references use some caches inside, and for example, if you type something inside a Java code block, it can possibly affect only the things that are inside that code block. And this cannot affect the method, the return type of the containing method, the superclass of the current class, and so on. So we have some special cache that is only invalidated when something outside a code block changes, something that could affect reference resolution in other files. It makes things a bit faster, but unfortunately it has its own issues because it's really hard to implement. Sometimes code blocks contain classes as well, anonymous or local, and in that case a change in code block is not anymore so harmless. And in some languages the method return type actually depends on the contents of the code block because it's inferred from that contents. So we're trying to move away from this cache and invent something else, something that really tracks the dependencies of each reference and clears them in a smart way, but we're still not there. And the current alternative approach, which everyone, I think, benefits from, is just to make the resolve very fast. And so even if you clear all the caches, the rehighlighting should still be fast. And we do it with the help of indices, which I'll talk about later. And interestingly, we have a very similar problem with our incremental build. We don't reuse the compiler, but we integrate with it. And when some files are changed, we obviously send them for a compilation, but then we have to determine which other files have to be recompiled as well, because they reference those files. And more importantly, we have also to determine which other files do not need to be recompiled, because nothing has changed. It's the same issue, but in the build, it's much, much easier. Thanks to the unified class file format, which is very, very nice, very readable. And the class files also contain references, but all these references are already resolved. They contain qualified names and argument types for the methods, and it's just a breeze. So much easier to work with. Unfortunately, the source code is much more complicated. Okay, what next? Oh, handling large projects. I like this part. So, the IDE, the IntelliJ project, basically with the code for all the IDEs that I showed you at the start, it's relatively large. It contains somewhat over 100,000 source files, mostly Java, and those files are split into several hundred modules. And for a compiler, the job is simple. You sort the modules topologically by their dependencies, take the first module, compile it, exit, then take the next module, compile it, exit, and so on. So you don't need to hold the entire project in the memory. But an IDE should work with the entire project, because at any moment, a user can ask, can you please show me the usages of something, or navigate to a declaration? And this doesn't care about modules. It can have the results all over the project. So we must somehow to handle that. And actually, I find it quite interesting that I have to give more memory to our build process than to my IDE. So the build process requires, the compiler requires more memory to just process some of the IDEs modules than my IDE requires to work with the whole project. So let's look at the specific challenges. For example, find usages. The problem is that PSI is quite nice, easy to work with. It contains comments, whitespace, and so on. But it also takes a lot of memory. And it actually takes more memory than a compiler syntactic tree would take, thanks to all these whitespace and comments and so on. So, we cannot afford to hold more than several tens or maybe 100 of parsed files in the memory. We don't have so much memory. But during find usages, we routinely have to scan over a lot of files and display the results from all of them. And these results should be correctly highlighted, so there's some PSI involved. So how do we do that? We do that thanks to a file-based index. We don't hold all the PSI of all the files in the memory, obviously. But when you first open your project, we load that PSI. We scan each of your project files, parse them, and then extract some important information from those files, and save them into an internal database called index. And those of you who've worked with other IDEs have seen this indexing process. And when a file changes, we also rescan it, also load, extract the new important information, and update the database. And this, by the way, means that the important information, whatever it would be, should only depend on the file contents. If it would depend on other files, then we would not know when to invalidate this cache. Again, the problem of cache invalidation. So we should not perform reference resolve during indexing. And so we don't hold the entire graph of all the declarations and references. We don't build it during indexing. And it would be invalidated on any change anyway. So what's an important information then? What do we save during indexing? It depends on the task. For find usages, it's just which identifiers does this file contain. We remember all of them, just in case. And when we are searching for usages of something, we take the name of that something and look at the files, get to the index and ask it to give us the files which contain this word. It works very well when you search for a class named abstract, spring, bean, factory, provider. But it works a little bit worse if you search for a method named add. Because there are many files containing this word. It's a Java standard library function. And it can be even worse with a method named getName, because not only it's a frequent method name, but in many languages also allow to use just the property name. So just the word name for it. And the word name is really, really frequent. So, yeah, don't name your methods add, or you will spend a lot of time doing find usages. We have some optimizations by using the compiled class files if they are up to date, but if they are not, then we are out of luck.
So after we get all those files, we get that was very cheap and easy query. Now it's time for expensive stuff, which is loading all those files, parsing them. We load the text, we find the actual place where the searched name occurs, and we parse the file fully or just around that place. Yes, we can also do this. And then find a reference at this place and check if it's really a reference to the thing that you're searching for. It can be that your project contains several classes named abstract, Spring, Bean, Factory, Provider. Why not? Several versions, for example. And if it's really a correct reference, then we extract all the information needed to display it, like syntax highlighting, the surrounding text, and we save it and display to the user. After that, we don't need the build PSI, which is, remember, memory hungry. We don't need it, so we just leave it sit there, and the garbage collector will eventually take care of it. And that enables us to search over hundreds of files. Okay, next interesting thing does not involve thousands of files, but it can involve hundreds. Because you might have only just one file open in your editor. And then obviously the IDE needs to highlight it and resolve the references. But those references can point to other files, and those other files, other classes can have their supertypes which need to be inspected. There are some method calls involved which also have return types which need to be inspected, and those return types also have supertypes and so on. And there's transitive dependency tree can easily also take a lot of files, and loading and parsing all this PSI, first, it can take a lot of memory, and second, it will just be slow, because parsing many files, even if our parsing is quite fast, it's still slow to parse many files. So, what do? We don't parse other files while highlighting just one file open in the editor. At least we try to. And for that we have yet another kind of index. I think it's the most important kind of index. It's called stubs. And it's basically the information about which declarations does a specific file contain. It's like class names, method parameters, return types, and the import statements to be able to resolve all of this, because the names are short and you are not allowed to do resolve during indexing. So you have to resolve at runtime by using the strings you just saved into the stubs. And more importantly, all those stubs do not contain anything that's not needed for resolve in the other files. Like code block contents, statements, expressions, white spaces, comments. This is all not there. And the stub tree looks like this. So we have, again, a small code sample. And here's a screenshot of the stub tree for that. So it contains just the essentials. For example, we have a file which contains a string with a package name. Then we have a class stub with a name and a qualified name, which is trivially computable from the package name and the class name. And then we have a modifier list stub. This stub tree has to be a subset of the PSI tree. So since we have a separate PSI element for the modifier list, we also have separate stub for a modifier list, but it's very small. It just holds a bit mask of the all possible access modifiers. And then this class does not have extended implements, but it has a method also with some modifiers. And the method has one parameters with the name args and type string array. And there is an empty throws list without any exceptions. So yeah, that's how stubs look like. And the good thing about them is that they don't occupy much memory. And we can easily hold thousands of them in the memory at once. And this enables us to do the resolve quite relatively cheaply. We don't have to parse all those files, we just load the stubs, and it just works quite faster. So it reduces the need to have the global model of all the references and incrementally update it. But there are still cases when we would be glad to have such model, because even with stubs, some queries like show me the inheritors of a class which has 10,000 of inheritors. So these kind of queries are still slow. And another thing, another nice thing about stubs is that they also implement the very same PSI interfaces. So the code analysis just works with the PSI class or PSI methods, the types, and it does not even care if those implementations come from stubs, memory efficient and fast, or the parsed tree, which is much more expensive. But that code must be careful to avoid invoking methods on that interfaces that contain information which is not present in stubs, like give me the statements in this method. This is not present in stubs, but there will be no exception if such code is called, but the actual file contents will be loaded, parsed, and the implementation will be transparently switched from stubs to the actual parsed tree. And this is not very bad, but it's expensive. So in tests, we have special assertions that to prevent such accidental changes, that we only load the parsed tree for files that are open in the editor, and not for any other files. So, and I think that's it. Congratulations. And a quick summary. So we looked at some challenges that IDEs face compared to the compilers. We looked at the feature challenges, that the IDEs should have the model they built based on the code. That model should be not very far from the original text to allow for changes. And the IDEs should also care a lot about white space and comments, and all of this is done by using PSI. Then we had a challenge that the IDEs should handle a lot of languages at once and how they interconnect with each other. We've looked at the references, at language injection, and how we support several JVM languages in one project. Then we looked at handling incorrect code, how the lexers and parsers should recover from errors to provide for helpful suggestions, and how the reference resolution and highlighting should be generous and should accept some invalid code, even if it highlights it, but it should still analyze it and report some issues and support for refactorings and so on. And then there was the performance part, when we saw how to reflect the modification
in the code model. We saw how our PSI is mutable, how we use global read, write, lock, and get user interface freezes because of that sometimes. We looked at how we update PSI incrementally by incremental reparsing and relaxing. And we looked how we fail to update reference targets incrementally and clear all the resolve caches on each change. And then we've seen how we use indices, normal file-based indices, and especially stub indices to allow to feed very large projects in not so large memory and to make things fast. And thank you for listening.
There we go. Okay. Thanks a lot. I really appreciate this talk, especially, I've spent, be thinking of your questions if you have any. We have a few on Slido as well. I really appreciate this talk because having just done some kind of toy academic IDE plugins, I've seen a little bit of the complexity that you guys must deal with. And I think this talk also illustrates the complexity that it really takes to do this kind of tooling in the real world. And it's just really impressive to look into. We're going to go ahead and open up the floor to questions. Does anybody have? Yeah.
Yes, also for me, thanks. The itch for building tools is always in me, but yeah, you kind of dampened it a bit because you show how difficult it really is. At one point in time, at 2 points in time in your talk, you mentioned that you have random tests which generate files and then parse them and then like that. Now, I teach my students that tests should be reproducible and always produce the same test. So if I hear random things, I'm a little bit suspicious. So doesn't that generate flaky tests then?
Well, first of all, I didn't mention that we generate random files. I mentioned that we take random files. Actually, we're in quite a convenient situation because we have a large corpus of Java files, which is our project source itself. So we just take some random file from our project, open it in tests, and do some random stuff in it. And you're right, it's kind of flaky tests. So on our build server, they are moved into a special configuration called exploratory tests that just find something. But once they fail, they print to you the minimal scenario needed to reproduce it. It's a concept called property-based testing, popularized by Haskell library QuickCheck, and we use this concept as well. But we have another library for that.
Thanks.
So many people in this audience will be building analysis tools and algorithms. Do you have any advice for them to integrate it effectively with the IntelliJ, make it work in a good way?
Well, it depends very much on what kind of analysis they do. If you have to process large projects, you might not be very efficient with using PSI, although it might depend, because PSI might contain way too much information for you. If you don't need comments, it's just a wasted memory. But on the other hand, PSI has an API which I find quite convenient, and for example, reference resolve is just one method call. So if you want to spare your time by concentrating on interesting stuff and not re-implementing the same compiler, or if you just want to do a prototype and don't care about performance, then
I would consider creating an IDE plugin and reusing this PSI, especially if it's supported by our IDE, like Java. So IntelliJ Community Edition, which is free and open source, it has support for Java, Python, Groovy, XML, HTML, I don't know, properties, plain text. Not sure about other languages. But you can also have a plugin to our commercial IDEs. They also have APIs. So for a PHP, you also can create a plugin. But it really depends on the task. I could give more advice if I knew the task more precisely.
Great, and I think we have a question back there while you're walking it up. One of the questions we're getting through Slido, why do you think JetBrains IDEs could be better than those by other companies? This is something I've wondered as well. For instance, why is ReSharper added to Visual Studio when they already have some functionality? I mean, I prefer ReSharper myself, but I'm curious to see what your answer is to this question.
Well, part of the answer is that we don't rely on the compiler and reuse it, and so we are more flexible in implementing all the cool features that we can. And the other part, I think, is that we are eating our own dog food, so we are using the IntelliJ on daily basis. I upgrade it every day to the latest master branch. And I quickly see what has gone wrong, what can be improved, and I don't hesitate to complain. And so we try to make the best tools for ourselves as well.
Great, and I think we had a question.
Thank you for the very interesting talk. So I also did a lot of parsing and program analysis, and one question is, do I need to write it always a plugin for it, or can I use it also as a standalone? That would be very interesting for us as a researcher because it makes integration just easier, and we are not, let's say, bound to the IDE, to the full IDE, but just to the part of doing parsing. Is that possible?
Yes and no. It's possible, but not easy. In fact, we have this in tests, but it's either very light tests that mock a lot of stuff, which are very suffering from, or those tests just load quite a lot of the IDE in the background, just you don't see it, but it's there. So this parsing requires some environment. It takes maybe a couple of seconds to load, but then you can use it. Does this satisfy you?
I didn't try it, but it means it's worth giving it a try. Because, for instance, Eclipse also is providing this, that you can use it standalone, and I think a lot of us are using the Eclipse JDD environment to parse Java source code.
Mm-hmm.
Another thing is also regarding how good is your resolution? For us, it's one important task is partial parsing. So that you have just a little piece of code, and how good is then a type resolution? You don't have a full class like we parse code on Stack Overflow posts.
Uh-huh.
Then you have just a limited amount of code, and still you want to get out the types of it, so that you can infer which class actually is referenced in that piece of code from the Android API, for instance. How good is that?
I see. Okay, we have an API for parsing a full-blown Java file with package and classes and so on. But we also have an API for parsing parts of Java file, like parse a method given a text, parse a code block given a text. And after that, you get some small PSI for that fragment. And if you want to resolve inside that fragment, it just works. If you also have reference some classes for JDK,
from JDK, it also works. But if you want to resolve to something else, you should also specify some context. So you say that this is a piece of Java code that is executed in the context of this class, and then everything available in that class will be resolved inside that fragment, and everything available from the imports and so on.
Great. I think we had a question right there. You go.
I'm wondering, how often do you consult this set of research? And could you give us some examples about where research could help you to improve or add some features to your work?
Oh, that's a complicated question. So, I frequently read some papers and think about how to adapt them. And I also, and my colleagues do the same. It's not very frequently that I actually adapt them. The most, I think, frequent kind of adoption is that I read a paper about some cool data structure that we can use in our internals, or more often it's someone else who reads this paper and implements it. On this conference, I found a lot of interesting things, but I think I have to think about them more before I can answer. In particular, I found it interesting that you have a lot of clone detection, and before that conference I didn't even know it's called so. In IntelliJ we have a similar thing, but it's called duplicate detection. Unfortunately, it's only in the ultimate part, not open source. It's also used using file-based indices. And I'm definitely going to share some proceedings from this conference with the guy who implemented these duplicates, because he's constantly in search of something better. But I don't think I can give you a general answer right now about all of it.
Great. And we have a couple more online. Maybe this will be the last one. I think, first of all, it's really encouraging that you are actually reading papers. This is kind of news to me. I don't know how many people in industry actually do that. So that's really encouraging. Did you happen to see one of the questions online, did you happen to see the missing curly brace paper yesterday?
Yes, I did, and I liked it a lot, and that's one of the things I'm considering to use.
Excellent. Well, I think that's a good place to stop then. That's very encouraging. I think we have a gift as well for our speaker. And as we come on back to the picture, let's give our speaker one more hand. All right, and coffee break is until 10:30, right?